Hello students, this is Dr. Anita Raj welcoming you for the very important topic of metallurgy, that is the refining process of crude metal. Okay. In the previous sessions, we saw the rest of the two steps of metallurgy, that is the concentration of ore and extraction of crude metal. And I am sharing you the link of these two videos in my description box for your perusal to have continuity. Okay students, shall move on to the topic now. So, refining of crude metal. Generally, the metal extracted from its ore contains some impurities like unchanged ore, other metals, then non-metals like silicon, phosphorus, carbon, and also some residual slag or flux, etc. Okay. So, the process of removal of these unwanted impurities from the isolated crude metal is known as refining or purification. Understood? So the process of removing the unwanted impurities. What are the unwanted impurities? Metals, some unwanted metals or unchanged ore or non-metals like silicon, phosphorus, carbon. Then some residual slags and fluxes will be there, is it not? So those things are the unwanted impurities, and the process of removal of those unwanted impurities from the isolated crude metal is known as refining or purification. Understood? Next, we are going to see the types of refining. Actually, under types of refining, we are having some five types, right? So, distillation, liquation, electrolytic refining, zone refining, and vapor phase method. Okay, shall see one by one now. So, what is distillation? Distillation. Actually, this method is used for low boiling metals. Okay, low boiling volatile metals. What if a low boiling volatile? Volatile means easily vaporizable. So then that also low boiling. So easily vaporizable metals that too that are having low boiling point. Okay. So for example, zinc and mercury. So for zinc, the temperature is 1180 Kelvin. Okay. For mercury, it is 630 Kelvin. Okay. So at this temperature, these metals will be getting vaporized. Okay. When it is heated, right? So what happens in this methodology? See, this is the apparatus we are making use normally in distillation. Okay. So this principle is used, distillation principle is used, but for large scale they will be using a very big apparatus, right? But here this is the disclaimer. The principle of distillation works like this. Here the impure metal will be taken in this distillation unit, and when it is heated, okay, when this impure metal is heated, the pure metal which is having the low boiling point and which is easily vaporizable will be getting first evaporated, and it will be coming out first, and it will be collected as distillate. Then after a long time only the impure metals will be coming out. Understood? So before that we will be collecting the pure metals, right? So in this method the impure metal is heated to evaporate and the vapors are condensed to get the pure metal as distillate. Understood? This is how the distillation process is carried out for refining this crude metal. Understood? Let us see the next methodology, that is liquation. Actually, what happens in this method is used for the low melting metals like tin, lead, bismuth, and mercury. Okay. Actually, this methodology is employed to remove the impurities with high melting point. Okay. See here, low melting metals can be purified by this method. So automatically, the impurities that are present along with this metals will be having high melting point. Okay. So for example, tin, which is having the melting point 904. Okay. For tin, so let me write here, for tin it is 904 Kelvin. Okay. 904. Then for a lead it is 600 Kelvin. Okay. For mercury it is 234. Okay, it is 234 Kelvin. Then for bismuth, so for bismuth it is 545 Kelvin. So the melting point of all these metals are very low. Okay, so for these metals we'll be following this liquation, right? So then what happens here is the crude metal will be heated to form a fusible liquid, and it will be allowed to flow on a sloping surface. See here, this is the setup, right? So this is the hearth, okay, or the furnace, right? This is the hearth or the furnace, right? So now what happens? The crude metal will be heated to form a fusible liquid, right? So here the crude metal, impure metal will be passed on, and it will be heated to make it more fusible or in the molten state. And it will be allowed to flow on a sloping surface. It will be allowed to flow on a sloping surface. That is, the impure metal is placed on the sloping hearth of a reverberatory furnace. This is a reverberatory furnace, and it is heated just above the melting point of the metal to be purified. Okay. For example, if you want to refine this tin, then the temperature should be given just above it. Okay. So 904, right? and it is heated just above the melting point of the metal in the absence of air. Okay. So now what happens is the salt, when it is heated, automatically the impure metal will be converted into a fusible state or a molten state, and it will start passing by. Impure metals will not be getting converted to a molten state because its temperature will be high. Okay, impurities. But whereas the pure metal which is to be refined will be having low melting point, so that will be getting converted to a molten state and that will be start to flowing. But the impurities which are in the solid state will be left behind the earth. So this is the earth, okay, and that will be left behind the earth. So the impure will be left behind the earth, whereas the pure molten metal will be flowing down towards the slope. Okay. So now what happens? The molten metal will be collected here at the bottom in a container, and finally it will be solidified. Understood? The next methodology is electrolytic refining. Okay. So what happens in the electrolytic refining? Actually, it is the process of removing the impurities from the crude metal by passing electric current is called as electrolytic refining. Okay. So here the process of removing impurities from the crude metal by passing electric. So here we are making use of electric current. Okay. So let us see what happens. First, let me explain the general methodology, and then I will be explaining with the help of silver extraction. Okay. So now methodology. The impure metal is made as anode. So which is made as anode here? The impure metal. Okay. And the pure metal is made as cathode. Okay. The pure metal is made as cathode. And the salt solution of the metal. Which metal? The metal to be refined. For example, if it is silver, then the electrolyte of that particular metal. For example, silver nitrate. Okay. So the salt solution of the metal acts as the electrolyte. Understood, students? So the impure metal will be acting as anode and the pure metal will be acting as cathode, and the salt solution of the metal will be acting as the electrolyte. Understood? Now what happens? On passing current, pure metal dissolves away from the anode and gets deposited at the cathode. See, when here this anode is connected and this cathode is also connected to an electric circuit, and when current is allowed to pass through the electrolyte, what happens? The anode, as I told you, it is made up of impure metal, is it not? So the pure metal which is present in the anode will start to dissolve away from the anode. It will be starting to move away from the anode and it will be getting deposited on the cathode. Understood? The pure metal from the impure metal will be getting dissolved into the solution and it will be passing on to the cathode and it will be getting deposited on the cathode. Okay. Now what happens to the impurities that are present in the anode? The impurities that are present in the anode will be settling as anode mud here. Okay, it will be settling as anode mud or anode sludge. Understood? So this is understood. So let me explain this process by considering the electrolytic refining of silver as an example. Understood, student? So here in the case of silver, the cathode, the anode will be cathode will be pure silver. Okay, here it will be pure silver. Okay, whereas anode will be impure silver. Okay, so anode will be impure silver. So what could be the electrolyte? It is acidified solution of silver nitrate. Okay, acidified solution of silver nitrate, AgNO3. Okay, acidified solution of AgNO3. Now what happens when a current is passed through the electrodes? The following reaction will be taking place. That is, the pure silver which is present in the anode will be getting converted to a positive. Okay, during electrolysis at the anode, the silver atom loses electrons. Okay, so what happens? Let me write here. The silver atom present in the anode, it loses electrons and gets a positive charge. Okay, it loses one electron and it gets a positive charge. Now what happens? The positively charged, this positively charged silver cations will be moving will be migrating towards the cathode. It will be migrating towards the cathode and get discharged by gaining the electrons and get deposited on the cathode. So now what happens? This Ag plus, that is the positively charged cation, will be gaining electrons, okay, from the from the cathode, and it combines with an electron and it gets deposited as pure silver on the cathode. Understood? So this is what happening by this. Okay, so hope you might have understood how the silver is refined from the impure silver. Okay, next process is zone refining. So what is the principle behind this zone refining? See, this process is based on the fractional distillation that the impurities are more soluble in the molten state than in the solid state of the metal. So, based on this principle, it's this zone refining is carried out. Okay, based on so let us see the methodology carried out here. Say this is carried out in an inert atmosphere. Okay, that's very important, right? This process is carried out in an inert atmosphere to prevent oxidation of the metal. So in order to prevent oxidation of the metal, they are carrying out in an inert atmosphere, and a noble gas will be used. Okay, helium, neon, like. Okay. Now in this method, the impure metal is converted into a bar. Okay, it's converted into a bar like. Understood. So the impure metal is converted into a bar which is heated at one end with a mobile induction heater. With a mobile induction heater or a circular heater. Okay. See here the mobile heater will be there. See this is the mobile heater. Okay. Here it will be the mobile. This is the mobile heater. And now this is the metal. Okay. Impure metal. And this impure metal is made into a bar, and now using this mobile induction heater we are heating this bar, okay, impure bar. When this mobile induction heater is moved from one end, from this let us consider this metal is heated at one end using this mobile induction heater, so that what happens is that particular end melts and forms a molten state. See, when we are keeping the mobile induction heater here, this particular area will be getting converted to a molten state. Understood? So what happens now as the heater moves forward, okay? Now as this heater moves forward, the pure metal crystallizes out because the pure metal will be getting converted into solid, and the impurities pass into the adjacent molten zone formed due to the movement of the heater. See here, this mobile induction heater will be heating this impure metal bar, and it will be moving, continuously moving from one end to other end. When it is moving, what happens? The molten state. See, this bar will be getting to converted to molten state, and again when it is moving, the next adjacent zones will be getting converted to a molten state. Okay. So what happens, as I told you earlier, the impurities are more soluble in the molten state. The impurities that are present in the impure metal will be getting converted to a fused state, and it will be moving from one place to another. So automatically the impurities present in the impure bar will also be moving along with the molten zone, and finally it reaches the end. Understand? And this process is repeated several times till the whole impurities are collected at one end of the rod. Understood? As after reaching this end, this this mobile induction heater will be moved again to the next end, and again it will be moved, okay, from this end to this end. So the rest of the impurities, if any of the impurities is left out, again that will be collected from this end to this end. Okay, and finally this end is then cut off, because at this end we'll be having the totally all the impurities. Okay, so now this end can be cut off and the impurities can be totally removed from the bar, and this bar will be having only the pure metal. Understood? See, this method is used to prepare the metals with high degree of purity, that is germanium, silicon, boron, gallium, indium. So all these metals are used for preparing the semiconductors. Okay. The next methodology is the vapor phase refining. So what's the principle behind this vapor phase refining? So it's based on the process of converting the crude metal into a volatile compound with a suitable reagent and moderate temperature, followed by decomposition of the same at higher temperature. See, actually what is happening here, the crude metal is first converted into a volatile compound by using a suitable reagent, and that too at moderate temperature. So after converting to a volatile compound, that will be undergoing decomposition at higher temperature to get the pure metal. Understood? So now we can understand this methodology or this principle by considering the following process. Okay. So we are having two types of processes. One is Mond's process and another one is Van Arkel process. Okay. So what happens in the Mond's process? See here, the impure metal is heated in a current of carbon monoxide. Okay, it will be converted. It will be heated in a current of carbon monoxide between 330 to 350 Kelvin to form a volatile nickel tetracarbonate. Okay, see here there's nickel is it's heated with, see this carbon monoxide. Okay, and that too at temperature 330 to 350. Is it not 350 Kelvin, right? It is heated. So it's getting converted to nickel tetracarbonate. So what happens now? The next step is decomposition step. Is it not? Now this nickel tetracarbonate complex is again heated to 450 to 470 Kelvin. So when it is heated to 450 to 470 Kelvin, this nickel tetracarbonate, which is volatile in nature, will be again decomposed to form the pure nickel. Okay, and we'll be removing this carbonate, right? So now the solid impurities will be left out. Okay, it will be left behind. So we'll be getting the purified nickel. So see the next process, that is Van Arkel method. This is used for refining zirconium and titanium. Okay, actually this method is based on the thermal decomposition of the metal compounds to give pure metal. Okay, thermal decomposition. Okay, see here we are using thermal decomposition. That means at high temperature this process will be taking place, right? And now titanium and zirconium can be purified by this method. Actually what happens is the impure titanium metal is heated in an evacuated vessel. It will be heated in an evacuated vessel with iodine at a temperature of 550 Kelvin to form a volatile titanium tetraiodide. Okay, a titanium tetraiodide. See here this titanium is heated with iodine at 550 Kelvin. Okay, it's heated with iodine at 550 Kelvin. We are getting titanium tetraiodide, that is volatile. Okay, now what happens? What's the next procedure? The metal iodide is then heated. See, that is metal iodide means the titanium tetraiodide is then heated electrically on a tungsten filament. Okay, now here it is heated on a tungsten filament. Here first what happens? Titanium is heated with iodine, and now what happens at 550 Kelvin? The volatile titanium tetraiodide will be coming out, and that will be allowed to pass through a tungsten filament. This is a tungsten filament. This is a glass tube containing a tungsten filament, and it's a hairpin tungsten filament. So now when it is heated, what happens? This titanium tetraiodide decomposes to give the pure metal. It gives us pure metal which deposits on the filament. See, this is the filament, tungsten filament, have this pink color, right? So now in this filament the metal will be getting deposited, that is the titanium will be getting deposited. Understood? So in the same procedure only, see here titanium is getting deposited. Same procedure we are using for zirconium also. So for zirconium, in the place of titanium you can use zirconium. So zirconium plus 2I2 on heating to 550 Kelvin. Okay, heating to 550 Kelvin, it will be getting converted to zirconium tetraiodide. Okay, now again this zirconium tetraiodide vapor will be passed through the this container glass tube which is fitted with a tungsten filament, and now when it is heated to 1800 Kelvin, 1800 Kelvin. Okay, here also it's heated to 1800 Kelvin. It's at a high temperature, is it not? Now what happens? The zirconium tetraiodide will be getting decomposed to zirconium and will get iodine. Okay, so this is the methodology we are following in Van Arkel's method. Understood, students? Well, fine, students. Hope you might have understood the topic which I have taught today. Let me meet you with another important topic in my next video. Until then, it's Dr. Anita Raj signing off from you. Thanks for watching.